Okay, thank you, and thanks for the invitation to speak, and thank everyone for coming after the hike. Okay, so yeah, I'll talk about the Hodge standard conjecture, so let me recall the conjecture. So fix. So let K be a field, algebraically closed field. And let X be a smooth projective variety over K, and we'll say connected. And D denotes dimension. And fix a polarization. So L is an ample line bundle. Okay. Now we have a cycle map, class map. Say Q coefficient to erratic étale cohomology. Yeah. And no. And here, so L is some prime invertible in K. Okay. And yeah, so this is codimension I cycle. Okay, so this is just notation, and I guess one more notation. So I'm not sure this is a standard notation, but let me write AI sub L X for the image of this cycle class map. So this is like algebraic classes in cohomology. Okay. Yeah. And then, so I fix polarization. So I take the primitive part of AILX. So inside AILX, we have primitive part. Say I is less than d over 2. Then we define the primitive part. I mean, this is just some elements killed by some power of Richet operators. So alpha C1L, this should be correct. Okay. Yeah. Okay, now I can state the conjecture. So the conjecture of Hodge type, or I mean, standard conjecture of Hodge type or Hodge standard conjecture is the following. So, so on this primitive part, we have a pairing. Defined by the following formula. So there is some sign to make it positive. Alpha, beta, and power of Richet operator. I mean, this is a degree. And so I regard this as a rational number. Okay, so this pairing is this pairing is positive definite. So this is a Hodge standard conjecture. Any question? Okay. So let me briefly explain what is known. I mean, I'll explain what my understanding. Okay. So, well, you know, if characteristic is just 0, then this reduces to the case of complex numbers, and you can use Hodge theory. And also for, say, surfaces, this is okay. So, yeah, so surfaces. And follows from Hodge index 7. Or you can also prove, the theorem for divisors. Okay. Yeah. So I guess these are only some sort of general results. Okay. But there are some special cases we can handle. And yeah. So yeah. So using this case of divisors, the middle proves the following. So let suppose X is abelian variety. And consider only cycles generated by divisors. But we also look at higher I. So you take the product of divisors. So in this case, you can prove the conjecture for, so conjecture is true for the part generated by divisors. Okay, so this is proved by Miro. And also sometimes you can lift your cycles to characteristic 0, and you get say Hodge class, then apply the Hodge theory. Then yeah, but I mean in general you cannot lift your cycle to characteristic 0. So and there is one recent result I'd like to mention. So this is a result of Ancona, and I guess this was announced in 2018, and I guess published last year. So this says, so X is abelian variety. And dimension is 4. And the claim is, yeah, I mean, he cannot quite prove the whole conjecture, but there exists infinitely many L for which Hodge standard conjecture holds. And perhaps I should say every L. So, I mean, and also in these cases, you can allow every L. Polarization. Okay. So, but I mean, in general, it is hard to prove conjecture is independent of your polarization. But because in this case you are in dimension 4, and somehow you can prove Hodge standard conjecture is independent of the choice of polarization. And yeah. Okay. And actually, yeah, maybe one remark here. You can formulate a different version using a numerical equivalent. So there is a numerical version. So you can consider numerical cycles and primitive ones. And you can, the conjecture is similar pairing is positive definite here. And what Ancona really proved is this numerical version is true for in this case. So maybe I write that. So he proved the numerical version for this abelian variety of dimension 4. And, sorry, I'm sorry. In this formulation, sorry, here should be, I think, algebraic closure of a finite field. And in this formulation, K could be any. I'm sorry. And why you can deduce this from this result? Well, there is a result of Kurzweil. There is numerical equivalence and erratic homological equivalence coincide for infinitely many L. So numerical equivalence equals erratic homological equivalence for infinitely many.
There is a question from Zoom.
Yeah.
Oh.
So I want to ask a question. So in the complex case where one uses Keller metrics, then one can also consider a real positive combination of C1L for ample line bundles, and so one has also some. So is there an analog of the real? So for real linear combination, positive combination of C1L. So let us say in the numerical context, I can perhaps formulate the same question in general. So is there something known about this? Or?
Well, yeah. Well, I mean, something is true, but yeah, I don't know precisely result. Yeah. Mention 3. Let me think. Yes, true. Yeah. I mean, all cycles are generated by device. Yeah, somehow. Yeah. And I'm sorry, in this result of Kurzweil, we need to assume this. Okay, any other question? Okay. So now let me state our result. Say theorem 1. So this is joint with Ito and Ito. So let X be a K3 surface over K. Then the conjecture is true for X times X. And as before, every polarization. But I mean, the dimension of this space is 4, and in this dimension, no problem happens. So yeah, so this is our result. And okay, so maybe I should have mentioned the left-shift standard conjecture. So I mean, Hodge standard there are two important standard conjecture, and Hodge standard conjecture is one of them. And there is another left-shift standard conjecture. And so, and in this case, so maybe remark left-shift standard conjecture for powers of K3 surface is known. I mean, this is easy. And so all standard conjecture is true for X times X. And, Hodge standard conjecture and left-shift conjecture together implies a Bayer conjecture, and this is a famous argument. And yeah, so in a sense, we verify such assumption, but in our proof, we did not try to avoid Bayer conjecture. I mean, it is perhaps possible, but we didn't try. Okay? So I mean, we didn't claim new proof of Bayer conjecture. Yeah. So how to prove this theorem? So this reduced to the case of algebraic closure of finite field. And in this setup, we have some results on the Tate conjecture and chain lifting. And that is the basis of our work. I mean, this is just a continuation of our previous work, or I mean, maybe we could realize sooner, but so let me recall our results. So recall our previous result. So let me formulate two theorems. So theorem 2. So this simply says the Tate conjecture is true. So maybe, sorry, I should fix. So fix some variety of finite field whose base changes X. Sorry. So we can talk about Garo action. Okay. So Tate conjecture, let me recall the statement. So the cycle plasma to the Galois invariant part is surjective. Okay. And so this statement is, of course, using the Tate conjecture for X itself. And the Tate conjecture for X itself was studied by many people. So, and we rely on it. So maybe I should mention that. So this is due to many people, and I cannot tell you everyone who contribute. But let me mention there's a work of Nygaard August in the case of finite height. And there's also, the most general approach was considered by Madap-Spera. And in fact, our proof of theorem 2 was inspired by their work. Yeah. Okay, any question? Okay. So what? I didn't understand. Uh-huh. So to prove theorem 2, we prove the lifting result. So, but well, I'll explain a statement in detail later, but let me now just mention same lifting exists. But I mean, this is a bit weak, and this is not enough to prove theorem 2. And we proved the refined version. And this refined version plays a key role in our proof of theorem 2 and also theorem 1. And I'll explain this later. So let me briefly explain how to deduce theorem 2 from theorem 3. So, well, there's a result on Hodge conjecture in this context. Well, so Hodge conjecture in this case, so if you have any Hodge isometry of, say, K3 surfaces of complex numbers, then your Hodge isometry is algebraic. That's the theorem of, Mukai. He initiated the strategy, and you can find the paper risking include generality. So, the proof of theorem 2 is just find the rift, apply Hodge conjecture, find the cycle, then specialize it. Okay? So, but in this argument, one actually should be careful. I mean, this is the basic structure of the proof, but let me caution that. So not all cycles lift. Or maybe, I mean, before you know the Tate conjecture, we can only talk about, I guess, Tate classes. And so, I mean, in the argument, we just show that sufficiently many classes lift. So still, so many Tate classes or cycles lift. And in the case of Tate conjecture, this is enough. So using Hodge conjecture, as I explained. But I mean, in this talk, our main theorem is Hodge standard conjecture. And but so this implication, I mean, as I explained, if you have a lift, then you know the positivity on this cycle. But and many cycles lift, but I mean, this is not quite enough to prove Hodge standard conjecture. Well, because not all cycles lift, and there is a subtle difference here. Okay. So I need to make some deduction, and I guess that's I mean, new in this proof. I mean, or that's something I did not realize when I was working on Tate conjecture. Okay. So well, yeah, I guess after I explain the refined version of same lifting results, then you will see what that means. Any other question? Okay. Oh, Frobenius?
Yeah.
It is easy. I mean, yeah, using Kugasato construction and semi-simplicity of Frobenius or abelian variety. Okay, so to prove theorem 1, I will use both theorem 2 and theorem 3. And let me first explain some consequences of theorem 2. Namely Tate conjecture. So the first point is, well, for this, actually I need semi-simplicity, he asked. So this here I use semi-simplicity actually. And the claim is numerical equivalence equals erratic homological equivalence for all L. And this is quite well known. Mm-hmm. Yeah. And so the second point is so let me decompose. So now I talk about motives. So this denotes the motive of the second cohomology. I mean, QNX projector exists, and I'm looking at second cohomology. So this is the motive. And I decompose it into two parts, so algebraic part and transcendental part. And because of the first point, I mean, we can work with numerical equivalence and erratic homological equivalence both. I mean, there is no difference. Okay. And now I look at endomorphism ring of the transcendental part. And well, so by a general fact, this is a, I mean, by working with, say, numerical motifs, by Jansen's theorem, this is a semi-simple algebra. But this algebra is actually division algebra. And whose center is generated by Frobenius. And this center is CM field. And well, this claim for the center is basically a direct consequence of the Tate conjecture. And this claim, this algebra is division. Well, this is easy and by, so look at crystalline realization. I mean, crystalline cohomology. Then there is some structural results on the cohomology of K3 surfaces, and you can just use to prove this endomorphism algebra is division. Okay, so this implies this transcendental motif X is simple in the, say, category of numerical motif. And similar claim is well known for complex K3 surfaces. But I'm working over, I guess, FQ bar, and I'm not quite sure about general K. Yeah. But anyway, this is what's going on. Okay. Anything else? Okay. So now I make some key deduction. I mean, I'm talking about the proof of theorem 1, Hodge standard conjecture. So our variety is just this product. And there is a natural involution, switching two factors. And this induces involution of this endomorphism ring. Denoted by this notation. And the claim is Hodge standard conjecture is true if and only if this involution iota is positive. that means trace of FTF is positive for non-zero F. This is a rational number. And this is actually easy. So there is a sort of trace formula. So if F and G could mention 2 cycles of product, then the intersection product can be written as sum of traces. Oh, maybe I should put T here. So this is a standard formula. And basically, I mean, if you look at the contribution from Tx, then this trace can be written using this trace. So up to positive constant, this contribution is just that trace. Oh, maybe, yeah. And we have intersection product here, and by comparing some sort of contribution from Tx, we can do this. I mean, we can prove this equivalence. Okay. Questions? So how to prove this positivity? And to explain our proof, I need to explain our results on CM lifting in more detail. So back to our results on CM liftings. So the key player here is a Kugasatake abelian variety. So fix some polarization L. Well, maybe I should use different notation, but anyway. We can touch abelian variety called Kugasatake abelian variety. And there are several variants, but we are not working with the one defined by Matsushibera, basically. And I cannot explain the construction. I mean, this is a hard part, but the point is, if you look at the primitive part of the cohomology, say erratic cohomology, and then this is a subspace of the endomorphism of the erratic cohomology of H1. Oh, wait. Yeah. Yeah, I mean, X and A are related in this way. And roughly, this H1 is a Clifford algebra of certain space. And the key result is a result of Kishin. So Kishin constructed a certain algebraic group. Let me denote it by IKS here. This is an algebraic group inside this endomorphism algebra. And so this is an algebraic group and defined over Q. And after they change it to QL, yeah, maybe I write here. This group acts on this primitive but by conjugation. By conjugation. And this is also kind of theta conjecture because you have something over Q. And what did I? Okay. So maybe I should now explain the refined version of CM lifting. So, I mean, but this is still rough, but it is like if you fix a torus, then the claim is like, I mean, so this acts on disk homology. And the claim is like, so this plus action on P2X1 lifts to, yeah, characteristic 0. Yeah. Oops. And so when I say sufficiently many is like, yeah, I mean, endomorphism coming from this action. Okay. And by varying T, like you get enough theta classes for which you can prove it is algebraic, and you can prove the theta conjecture. Yeah. Okay, so, and to prove the Hodge standard conjecture, we actually need a right variant of our previous result. So let me call it 7.4. So now the claim is there is a surjection from this group IKS to say ITX, and this is just a group defined by endomorphism ring of Tx and involution. So namely, this is defined by this equation. So this is like sort of motivic isometries. And yeah, so the construction of the map itself is non-trivial, and we can further prove this is surjective. Okay. And the proof of this theorem 4 is quite similar to our proof of the theta conjecture. Because, like, I mean, given the element of IKS, we take a lift using theorem 3, then apply Hodge conjecture. Then you can somehow construct a map. Questions? So you can define some sort of erratic counterpart easily. and using site like Frobenius there. I mean, it's like Frobenius centralizer. But the claim here is like the group of defined of QL descend to Q, and there is no description of IKS itself. Over what? Mm-hmm. Any other question? Okay. So now, I mean, we can finish. So this group IKS is actually has a nice property, and if you look at the real point, then this is compact module center. And this follows from the positivity of the product involution. But my map is surjective, and well, there's slightly more we can prove. And at the level of real points, it is still surjective. So real points of this group is actually compact. I mean, this map kills center. But this compactness is equivalent to the positivity of the involution. So this is a rough outline of the sketch, rough outline of the proof of 7.1 Hodge standard conjecture. Okay, so I still have some time, so let me discuss the related results. So there are a few things we can prove. So, for instance, we can treat the Hilbert scheme of 2 points. In X, I mean, X is K3. And I mean, this Hilbert scheme is very close to the product. And I mean, there is a difference, but we can manage. Okay. And well, other case, I mean, so it is natural to ask Hodge standard for conjecture for higher powers. And we cannot prove this in general, but under the assumption, so I'll put a condition on Picard number. So Picard number is always less than or equal to 22. And I assume this is greater than or equal to 17. So why this case is okay? So we can, I mean, here any k. Okay, but then again, we just work with FQ bar. And if k is FQ bar, then actually this inequality implies a stronger one. So this implies Picard number is greater than or equal to 18, because by the Tate conjecture, Picard number is even. And in such cases, the field generated by Frobenius So this is a CM field generated by Frobenius. Has degree 4 or 2, right? I mean, I'm talking about Frobenius acting on Tx. And the size of Tx is 4 or 2. Or 0, yeah, actually. I mean in the super singular case, there is no transcendental part. And everything is algebraic. Anyway, so let me only consider this case. And a trick here is, so eigenvalues of Frobenius can be written as like alpha, beta, alpha inverse, beta inverse, and they're different. Something like this. And exercise is there is no non-trivial relation, namely, well, no non-trivial multiplicative relation. So I mean, the trivial one is alpha times alpha inverse is like that. Okay, and I think this is at least noticed by Zahin in the context of abelian varieties. I mean, similar Frobenius appear there. Okay. And this exercise tells us like Tate classes Tate classes in higher powers. We are considering higher powers. Just controlled by Tate classes in X2 or X. Because there is no, I mean, to get an extra Tate cycle, you need a non-trivial multiplicative relation. So we just use Hodge standard conjecture for X2 and X. I mean, there is a non-trivial argument actually in this reduction, but you can do that. And if Picard number is smaller, then non-trivial multiplicative relation can appear, and it's harder. It's almost time. So these are, I think, what we proved for usual Hodge standard conjecture. That, as I mentioned at the introduction, there is a numerical version, and Ancona proved the numerical version for abelian fourfolds. And so we can ask if the numerical Hodge standard conjecture holds for like higher powers without, under more general, case. Because I only have 5 minutes, so let me only state. Let me first state the results. Well, this is actually a special case. We actually have not yet worked out what we can really prove, but at least we can prove this. So 7. So again, X is K3. And now assume Picard number has a form of 22 minus 2p. Say defined over SQ bar. And say 22 minus 2p. And here p is, well, you can allow 2, but 3, 5, 7. Well, you can also allow 2, 7, but this is easier. And in this case, the numerical version of the Hodge standard conjecture is true for all powers. and polarization. So key input is Ancona's theorem. I mean, for say like general motives of rank 1, general motives of rank 2, sorry, and this leaves over some ring of integers of a periodic field. So, I mean, a strategy of Ancona is just find a rift and apply the Hodge theory. You have a positivity of the quadratic form, and if your L is different from P, then there's comparison between vertical homology and radical homology. And he also controls the crystalline homology using periodic Hodge theory. And using this rank 2 condition, somehow he proves the positivity of the quadratic form of numerical cycles. Okay? And the point is, and another point of our theorem, or actually there is another, I also proved the version of Ancona's theorem. So Ancona consider abelian fourfolds, but I consider like abelian variety of prime dimension. And in such cases, like you see a prime. The point is, so in this exercise, there is no non-trivial multiplicative relation. But in this case, you just get only one non-trivial relation. And and such a one non-trivial relation gives you this rank 2 motive. Yeah, more or less. And we can apply Ancona's theorem. Yeah, I'll stop here.
Are there questions or comments? Yes.
So it seems like a lot of the specific results that you needed to prove your main theorem only make sense in this particular context, at least it seems to me. But the result that you proved about the lifting, the refined lifting, that seems to make sense in a much more general context. Do you have a sense of whether or not you might be able to adjust the method to work in any other cases?
Well, not sure, but maybe we can talk about like hyperkähler varieties of some deformation. You first need to, there is some definition, but you first need to define suitable class of hyperkähler variety defined over finite field or something.
Okay, thank you.
Another question or comment? Maybe? Something on Zoom? No question on Zoom. So I think we can thank the speaker again.